All right, our next speaker is Peter McMahon. He's a PhD student at Stanford University where he works on implementations of quantum cryptography, and he's going to give us an introduction on this topic today. So thank you very much.
All right, thank you very much. So first of all, I'd like to thank the organizers for organizing this meeting and for inviting me to come out here to tell you a little bit today about basically an introduction to quantum cryptography, which is one of the subfields of quantum information that I think is probably most easily accessible. So that's why I chose to talk about it today. So I'm going to start off with an overview of how we imagine that quantum cryptography might be able to be used in the context of one-time pad cryptography. And I'll explain a little bit about what that is and how, if you want to use one-time pads, you have a so-called key distribution problem. And this is actually the problem that quantum cryptography solves. So in order to explain how quantum cryptography works, I have to give you a little bit of an overview of quantum mechanics, and I'm going to give you a really short course in quantum mechanics for those of you who haven't studied it at college before, but I'm only going to give you the pieces that you need to know to understand the talk. So of course I can't cover everything you would cover in 2 or 3 years of quantum mechanics in half an hour, but I'll give you the sort of highlights of quantum mechanics that allow quantum cryptography schemes to work. And it's actually sort of fairly surprising how simple it all is. So it's kind of neat that I hope that those of you who haven't seen it before will come out of this talk today at least with some sort of intuition for how the laws of nature on the sort of atomic level actually allow you to build a cryptography scheme. Then I will discuss, well, interleaved with this, I will discuss 2 quantum key distribution protocols. The first one is one that's 30 years old, from Bennett and Brassard from 1984, which is a protocol that uses only properties of single photons. And with this protocol, you can do quantum key distribution without really much fancy business at all. And so this is a nice demonstration, and it turns out that if you've heard of commercial quantum cryptography companies, they basically all implement this BB84 protocol. So I won't cover all the details of how you really make it secure in practice, but I'll try to give you the physical intuition for how it works and tell you a little bit about what kind of components there are inside an implementation of this scheme. Then I'm going to talk about another protocol called from Eckert in 1991, and this protocol works basically in a similar way to BB84, but it uses another property of quantum mechanics that I'll introduce called entanglement. And this is also kind of a cool demonstration of some feature of quantum mechanics that's not really present in the classical world, but that somehow allows us to do some neat information processing task. I'll also talk a little bit about Bell's inequality and the connection to the Eckert 91 protocol. So for those of you who've looked at the program, you may have seen that there's a hackathon going on at the moment, where some guys are trying to use spare parts borrowed from all over the place to try and do a demonstration of an experiment where they try to basically violate the so-called Bell inequality. But apparently no one's given a talk here yet or an introduction to the rest of the audience about what the Bell inequality is and what Bell's theorem says, so I'm going to give a little bit of an overview of this as well. And hopefully that will inspire you to go take a look at the experiment that these guys are building in the room next door, in the building next door. And then I'll have a very short piece on long-distance quantum key distribution, because if you've followed at all what's been happening in quantum communication for the last 10 or so years, you will have noticed that a bunch of companies have sprouted up building QKD solutions, but all of them seem to only work over a limited distance of up to 100 or 200 kilometers. And I'm going to explain a little bit of why this is and how this distance limit can be overcome, potentially. So first of all, I'll talk a little bit about some classical cryptography. So there's this idea in classical cryptography, I think maybe originating in the late 1800s, that a so-called one-time pad will provide perfect security. So what this means is that if you take your encrypted text, if you've encrypted it with a key in a way that I will describe, and you only use that key once, then you in some sense get perfect security in that the encrypted message provides 0 bits of information about what is contained in that message. Basically, the only information that an eavesdropper would get if they intercepted the message was some limit on how long the message could possibly be. But a very important point about this is that one-time pad cryptography is only perfectly secure if you use it one time per key. You must not reuse a key. Otherwise, people can start to do some statistical analysis on the messages and start to glean information. So I've taken an example from Wikipedia here, and it's a very simple protocol, so I'll walk you through it. If you want to send the message, for example, hello, you can imagine having some encoding for the letters here. The simple encoding that they use in this example is just where A is 0, Z is 25, and so on. So your message is now numbers. And now we imagine having some key, and this key must be completely random, and we're only allowed to use this once, but the key is just this string that's the same length as the length of the message. That's also important. And what we do is we take this key and we add it to the message. So we get now this set of numbers, and we then perform modular arithmetic. So our alphabet is 26 characters long, so we do this mod 26. And then the outcome of this is the ciphertext. This is the encrypted text that we're going to send over our network to the person that should receive the message. And if somebody intercepts this, unless they know the key we used, they cannot decrypt this message. They can find hello if they try all possible combinations of keys, but then they can also find many other plausible possible messages, so they get no information. So how does the decryption side of things work? Well, if you start with the ciphertext, and you now, of course, this has this number encoding, you then subtract the key, and you perform modular arithmetic again, you basically end up getting your message out again. So okay, this scheme performs as you would expect. You can encrypt a message and you can decrypt it. The problem is that you have to use, you have to have a number of keys that basically is the length of your message, and every time you want to send a message, you have to use a new key. So you have a large problem now of you need to distribute keys to all the people you want to communicate with. And this is a feasible problem. It's just logistically somewhat annoying. And this photograph here shows a code book from the KGB. During the Cold War, they distributed this within their spy network, and these guys had these tiny books full of one-time pad keys. This is kind of an annoying solution, and now if one of these code books gets compromised, you somehow have to come up with a way of sending the person the new code book. But if you didn't trust the channel, that basically means you have to physically move things around with people with guns, and that's not an ideal solution. So is there some way to do this without using some physical hardware, like a hard drive or a book? And obviously you could think about, well, is there some way we could do it with maybe a classical network? But of course, if your classical network was secure in the first place, you wouldn't need encryption. So that on its own doesn't work. So for a long time, one-time pad cryptography seemed like a great solution to making perfectly secure cryptography, but one that was logistically infeasible unless you had very, very large, demanding security needs. And consequently, we have the advent of public key cryptography and so on that provides the security that we use today, which relies on proposed impossibility or infeasibility of, for example, prime factoring and other supposedly difficult problems in mathematics, but they don't provide perfectly secure communication. So what can quantum mechanics do to help us with this? So what I'm going to do is I'm going to introduce some features of quantum mechanics that will let us discuss this first protocol that I told you about, the Bennett and Broussard one. So Some features of quantum mechanics that are kind of interesting are, one is that quantum objects can exist in superpositions, and I'm going to have some slides on what this means for those of you who haven't seen it before. And when you measure a quantum state or a quantum object, it will give you a single answer back. So if the quantum object exists in some superposition, you can measure it, and it will not give you both the possible states. It will give you just one of them. And again, with examples, this will become clearer. Another crucial feature of quantum mechanics for the quantum cryptography schemes is that measurement causes the state the object to collapse to the state that you measure. And then finally, I'll discuss this interesting property of quantum objects called entanglement, where quantum objects can be connected in some kind of way that yields correlations between the measurements of them that are not explainable by classical means. So let's do some examples to try and make this a little clearer. So first of all, I'm going to talk about, for the rest of the talk, basically about photons. So most of you, I guess, know that a photon you can basically think of as being like a packet of light, so a discrete blob of light. And one property that's associated with photons is polarization. And I guess everybody who studied electrical engineering here, and certainly those who studied physics, will have seen polarization before in an electromagnetics class, where polarization just refers to the orientation of the electric or the magnetic field of the propagating electromagnetic wave. And you can think of a photon, for example, being either horizontally or vertically polarized. Of course, it can also be circularly polarized or elliptically polarized. But I'll discuss things in terms of this horizontal or vertical polarization for most of the time. So if you haven't seen polarization formally before, you might have come across it, for example, in sunglasses. There's a light that's reflected often has some polarization, so if you use polarized glasses, you can block out reflections from sunlight off water. And if you've seen some description in a physics class a long time ago and need just a little bit of a reminder, here's a diagram showing sort of the out of phase electric and magnetic waves that you have when you describe an EM wave, which is, well, a photon is a quantized unit of one of these waves. So let's imagine that we have a photon and it's horizontally polarized. So to introduce some notation that's going to be used throughout the talk, we will say that the state of the photon psi is given by this funny-looking notation, just h, with this vertical bar and angle bracket is just the Dirac-Brocket notation. It doesn't mean anything besides just that this is when you see that notation, it means we're talking about a quantum state. So it could also be vertically polarized, in which case we would describe the state of the photon as psi equals v. And as I mentioned before, quantum mechanics allows us to say that actually the photon can be in some arbitrary superposition. So it doesn't have to just be horizontally polarized or just be vertically polarized. We can have an arbitrary superposition where we have some coefficient here alpha and some coefficient here beta, which describe basically how horizontally or how vertically polarized this is. So far, this is nothing too special because you essentially have the same thing in classical optics when you have a Poincare sphere. So if you've seen this before, this is the same story. You can describe the polarization state of an electromagnetic wave in classical electrodynamics by describing it in terms of this vector with the basis states of h and v. So let's suppose that we have a photon in some state that's an arbitrary superposition with these complex coefficients alpha and beta. And let's suppose we measure the polarization of the photon. So we're going to ask the photon the question, what is your polarization, H or V? So what will happen in this measurement is that you will get an answer that it is horizontally polarized with probability alpha squared, and you'll get the answer that it's vertically polarized with probability beta squared. So from this, you can see that we must have the relation that alpha squared plus beta squared equals 1, because when you ask the photon, are you horizontally or vertically polarized, it's going to give you either the answer H or the answer V. There's no third option here. So this normalization condition must hold. However, there's nothing to say that there's something really special about the horizontal and vertical polarization bases. And in fact, the choice of basis is basically arbitrary. And we could imagine describing either the preparation of the state or the measurement of the state in some other basis. For example, we could talk about the diagonal and anti-diagonal basis, where if you have this sort of plus 45-degree polarization and minus 45-degree polarization, we can describe these states here, or the diagonal state like this and the anti-diagonal state like this. So what happens if we measure a photon that's prepared in the state D, if we measure the polarization of this photon? So if we ask this state, are you horizontally or vertically polarized, what we'll see is that in this basis, you will, if you ask it, are you D or A polarized, you'll get the answer D 100% of the time. But if you ask it whether it's H or V polarized, you will get a non-deterministic answer. You'll get H 50% of the time and V 50% of the time. A very crucial part of this, though, is that once you've measured it in this basis and you've gotten an answer, the state will actually collapse. That means that if you start off with a diagonally polarized photon and you measure it in the HV basis and you get the answer H, the state will actually become horizontally polarized. So then if you ask it again what its polarization is in the HV base, it will then always give you the answer H. So that's a very interesting feature, and is something that we're going to exploit. So a side note of all this is that this actually provides an interesting way to make random numbers. Because let's say you start off with a diagonally polarized photon, and you measure it in the HV basis. You're then going to get the answer that it's horizontally polarized with probability 50% and vertically polarized with probability 50%. Let's say you do this, okay, and you get the answer H, and it collapses to H. Okay. So now you now essentially have one binary number if you think about the answer H or V as being 0 and 1. Now you can do it again. You make another photon that's diagonally polarized, and you ask, is it horizontally or vertically polarized? If you do this, maybe this time it gives you the answer V. You do it again, this time it gives you the answer H. You do it again, this time it gives you the answer H, and so on. And so in this way, you can actually use a source of single photons that are polarized as a random number generator. And that is quite connected to the BB84 scheme. So what I'm going to do now is go through a little animation for you that tries to explain how the BB84 protocol works. And in the following animation, which I've pilfered shamelessly from Aaron Defender, who was at UIUC when he made this, is this notation that's shown up here, is that we're going to be doing things in two bases, which are the H and V bases. So that's the one that's designated as the plus here for V and H. And then there's this diagonal and anti-diagonal basis where you see these diagonal and anti-diagonal lines. And in the notation here, basically, the horizontal polarization is a 0, and the vertical polarization is a 1, and the diagonal polarization is a 1, and the anti-diagonal polarization is a 0. So the way the protocol starts is the following. We have a sender, Alice, and a receiver, Bob, and the idea is that we're trying to share a random bit string between these two entities in a way that if an eavesdropper is eavesdropping on the channel, that we can detect it. So at the end of the day, at the end of the protocol, what we want is that Alice and Bob should share some random string, a random bit string. And the way that this works is that there's a quantum channel here between Alice and Bob, and this in this channel, what we're going to do is we're going to send photons that have some polarization. And Alice starts off by deciding randomly to either polarize photons in either this diagonal basis or in the linear basis. And So there's a choice of basis that happens for however many bits she wants to send. And so each one, this string here basically is a random bit string that must be made in a completely random way, otherwise the protocol is insecure. And for example, one way to do this is using the quantum random number generator scheme that I just showed you. Then she also chooses another random bit string. And what happens here is that she's then going to transmit states as follows. So if she chose that the first bit that's going to be sent here is in this diagonal basis, and that the state that must be sent is the 1, then she'll transmit this state here. And then on the next one, she's going to use this basis and use data bit 1, which was the vertical state, and again this basis, data bit 0, which was the horizontal state, and so on. And these are going to be transmitted and then received by Bob, and Bob's going to do something with these. So the first thing that happens in the protocol after Alice has made these choices is that Bob then, Bob can simultaneously make, again, a random choice of basis, or bases, that he's going to perform his measurements with. And you'll note that this set of bases is different than Alice's because they independently produced random strings. So, of course, with high probability, they're not going to be the same. Not that it would matter if they were. And then we begin. And Alice starts off by sending this very first state. So boom, 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 it goes down the optical fiber, for example, or over free space and microwave, if you like, but typically we imagine in practice doing it with optical fibers. And Bob then measures the received state in the basis that he chose for the first received bit. And since Alice sent this state here, which was in the diagonal, anti-diagonal basis, when Bob receives it, of course, he gets the same answer as what Alice sent. So she sent a 1 in this basis, Bob measured in that basis, so what he receives is a 1. Then they do it for the next state, which is this one here. So Alice sends this state here, Bob is now measuring in a different basis. That means Bob will get a random answer. Then we do it for the next bit. It's sent in this linear basis. Bob is receiving in the linear basis, so he will then definitely receive the same state and the same data bit that Alice sent. And we repeat this for all the bits. Then, now that this is done, Alice and Bob communicate over a classical channel and tell each other which basis measurements they were doing. So Alice tells Bob which bases she prepared each state in, and Bob tells Alice which basis he measured each of the states in. And what they will do is when they randomly happen to choose the same basis, they will keep those data bits and they will throw all the other ones away. So they communicate, for example, for the first one over this classical channel that Alice chose to prepare it in this basis, Bob chose to prepare it in the same basis, so okay, this data point we keep. Then for the next bit, Alice prepared it in the linear basis, but Bob measured in the diagonal basis, so we throw that one away. We discard it, it's not useful. Then we go to the third bit. Alice prepared in the linear basis, Bob received in the linear basis, so this one we keep, and so on. And after they've finished with this procedure, what they will be left with is all the data bits where Alice and Bob both use the same basis. And you will see here that these strings are exactly the same for both of them. So somehow now what we've managed to do is produce a random string at this physical location in space where Alice is, and have that random string appear where Bob is, even though we didn't just directly send the string. And we did it in a way that an eavesdropper can be detected. And there's a way, and the way you can detect the eavesdropper is the following. The final step of the protocol is that Alice and Bob want to now make sure that nobody was listening in to what they were doing. And what they do to do this is they take some subset of these random strings that they have, and they check that they definitely match. Because by what I've just told you, they should match if no one interfered. But if some eavesdropper Eve was listening in and trying to then repeat the signal back to Bob after listening in on it, Eve will necessarily have made some mistakes because she doesn't know which bases that Bob is measuring in, so she has to guess. And if she guesses, some of the time she will guess wrong, and so with high probability, if you do this for some reasonable length of string, you will be able to detect interceptions. And so that's the final step of the protocol. And once Alice and Bob have agreed over this classical channel that none of the parts of the key that they shared are different, they can then conclude that there was no eavesdropper, and then they can safely use the rest of the string as a private key, or a set of private keys. So that's a pretty neat protocol, and it doesn't really use very much fancy. All you really have to implement a very basic version of it is a single photon source. So you need something that makes single photons. It's really important that you produce single photons rather than, for example, weak Gaussian states like a regular laser produces, because one of the key features of the security was provided by the fact that if Alice measures the photon state, that she will disrupt it. But the problem with some coherent state is that if it's possible that Alice can tap off a bit of the state and not affect the part that's going through to Bob. So it's really crucial that you use a single photon source, at least in the simplest view of things. You need polarization optics, so nothing too fancy there. You need to be able to polarize your photons. You need to have some wave plates to rotate the polarizations that you can do either linear basis or 45-degree basis. And then you need some single photon detectors. So the equipment inside a commercial quantum cryptography device is actually not particularly complicated. The main difficulty really is this single photon source. That's not something that you can easily produce, but there are companies that actually produce commercial versions now, and many research groups worldwide have single photon sources. So that was one protocol. This protocol in 1984 got people really excited about the possibilities for using quantum mechanics for cryptography, and there was around the same time a bunch of people thinking about how to use quantum mechanics for computation. And one of the things that came up is people started to realize that another feature of quantum mechanics, entanglement, can be very useful. So I'm going to now try to tell you a little bit about what entanglement is. So let's suppose that instead of just having one photon that we're sending, now we're talking about having two photons. We're going to just try and describe quantum mechanically what is the state of two photons. And so the most general way you can describe it is the polarization state of two photons is the following, is that we have our state of the two-photon system here is described by an amplitude for the state to be in the first photon being horizontally polarized and the second photon being horizontally polarized, the first photon being horizontally polarized and the second photon being vertically polarized, the first photon being vertically polarized and the second photon being horizontally polarized, and finally the state where the first photon is vertically polarized and the second photon is also vertically polarized. This is nothing too surprising. If we're saying that both photons can be either H or V, of course, there are four possibilities. So we have four basis states here, and we haven't provided any restrictions on this yet, so they can have arbitrary amplitudes just so long as the square of these numbers sums to 1. So let's imagine that we don't use the most general state. We just use one where we have either the first and second photon are both horizontally polarized, or the first and second photon are both vertically polarized. You can now imagine if you can make this state where we have two photons, and let's say they propagate away from each other, and they have some polarization each. You can now, if they're prepared in this state, you can ask the question, well, what is the polarization of the first photon? For sure, if you ask it in the linear basis, the result will either be H or V, because it's either H or V. And let's suppose that the result is of this measurement that you do on the first photon is horizontal polarization. What is the result of the collapsed state of the system? So I've told you before with the single photon case that once you measure the state, it will then collapse to the measured result. And the same is true here. But now something really interesting happens, because even if you only measure the first photon, the state will collapse to this. And what you see is that even though you measured the first one only, somehow the second photon has also become horizontally polarized, even though it started off where if you measured the second photon, there would be some probability of it being vertically polarized. That's kind of interesting. And so the sort of funny artist description of what's happening here is that somehow, even if you have a photon here and a photon here, and they've propagated away from each other, so they separated in space, that somehow they're in some way connected, which is a very strange notion. So we say that this kind of state is one where the photons are entangled. And one of the features of an entangled state is that a measurement on one of the particles seems to affect the other particle. And people argue about whether it's really affecting it or whether there's some other sort of philosophical explanation for what's going on, but certainly it appears to affect it. This seems really counterintuitive. It seems like this is probably some kind of mistake, but it turns out that people have done these kind of experiments and that they work out. And this was actually one of the features of quantum mechanics that Einstein was really convinced, suggested there was something fundamentally wrong with quantum mechanics and that we needed to develop a new and different theory. This is the title page from a physical review paper that Einstein wrote with Podolsky and Rosen in 1935. And he never, until his death, accepted quantum mechanics, and one of the main reasons was this sort of strange counterintuitive behavior that you can get. But it turns out that this really seems to be how nature behaves, and people have verified this experimentally many times now since the early 1980s. So this entanglement feature is kind of strange, but one of the neat things about it is that Eckert figured out how to use it to distribute random numbers between two parties in a different way than Bennett and Borsard did. So let's suppose that you prepare two photons in this state. So the state has 50% probability of both photons being H, or 50% probability of both photons being V. So if you measure it, you will either get the state out here, or with 50% probability, you'll get the state out here. So we can try use the same trick again as BB84, where Alice and Bob randomly choose bases, and they measure either in the H and V basis or the D and A basis, and they will then get correlated answers, because as you may, if one of these photons goes to Alice and the other one goes to Bob, you'll see that every time you produce this state and then Alice and Bob measure, they either both get H or they both get V. So now the random number that gets produced is correlated, it's connected between these two locations. And they should do this with randomly chosen bases, so that if Eve interferes, then Alice and Bob will see some inconsistent results. If they don't change the basis, then it will be possible for Eve to intercept and reproduce the states, and then they wouldn't be able to detect it. But if they use the same trick as BB84, then this problem goes away. So what do you need to be able to implement this kind of protocol? The main difference is that now somehow you need not just a single photon source, but you need an entangled photon source. You need to somehow have a way of making photons in this state here. And that's not an entirely trivial thing to do, but it turns out that people have developed ways of doing it, and I'll show you in the next couple of slides one of the ways that people have developed. You again need a bunch of polarization optics and detectors. So one of the most common ways people produce entangled photon states is using so-called spontaneous parametric down conversion in Chi2 nonlinear crystals. And the idea of this scheme is the following, that if you put in a strong pump laser beam into one of these crystals, what will happen is you'll have some photon be absorbed, and then two photons are emitted that are each at half the energy of the single photon that was absorbed. And there's momentum conservation and angular momentum conservation And this results in at least in some situations, a case where you can pump the crystal and get out two photons that actually have correlated polarizations. It also turns out that they will come out at different angles in the case of a BBO crystal, and if you collect the photons within the cones that the two different photons come out of, you cannot distinguish which they are from the spatial information, and so you end up having photons that are coming out in a state that is actually entangled. And this is what the guys in the hackathon are using. So if you want to go see some part of a setup that actually does this, I encourage you to go check out the hackathon setup sometime after this, whenever the next break is. So besides doing this ECRIT 91 protocol, one of the things that you can do with this kind of two-photon source that produces entangled photons is try to check one of the predictions of Bell's theorem. And Bell did the following. So what I'm going to show you here is now, unfortunately, slightly different notation than what I've used in the rest of the talk, but I'll try and point out where I've made changes. And Bell's theorem is often given some kind of mystique, but I'll try and give you a very simple description of Bell's theorem and where the so-called Bell inequality comes from. So consider that we have two parties, Alice and Bob, and they make an Alice, and you send an entangled state, or you send a state to Alice and Bob, so some two-particle state, and Alice can make a measurement on the particle that she receives in either the basis A or A prime, and Bob can choose to make a measurement on the particle he receives in either basis B or B prime. And for the purposes of the following discussion, we're going to do everything where the measurement outcome can either be -1 or +1. So up until now, I've been talking about H and V, or D and A, or 0 or 1. Imagine here that the two possible outcomes have outcome either -1 or +1. It's not super important that this be the case, but it's important that we keep the definitions constant because the functions I'm about to define rely on them. So Bell started off saying that let's suppose we have this setup with Alice and Bob, and then let's make two assumptions about physics and see what the consequences of these assumptions are. So the first assumption he made is something called local determinism, and this is a pretty intuitive notion. He's saying, let's suppose that physics works in a way that when Alice measures the particle that she receives at her location in space, that the outcome of her measurement does not depend on what happens somewhere else in space. It only depends on what she's doing and where she is. And similarly, that when Bob makes some measurement at his location in space, that the outcome of the measurement that he does not depend on something else that's happening somewhere else in the universe either. And this seems like kind of an obvious statement to make, and it seems pretty intuitive to us. If I look at this piece of paper here and look at what color it is, it shouldn't matter what color some other piece of paper somewhere else in the room is. It should only matter what's happening here. The other assumption that Bell made is something that's often referred to as objective reality. It goes by a number of other different names, but the idea is the following, is that we also have some sort of intuition as humans that if we get given some particle and we're going to measure some properties of it, and we could choose to measure either in this basis A or A prime, that if we measure in basis A, that we'll get some answer, but even if we measure in that basis, there is an answer in basis A prime, that it's determined, just we didn't measure it. And similarly for Bob, if he can measure in B or B prime, and if he chooses to measure in B, even though he's done this, that there really are answers for the measurement basis B prime too. We just haven't answered them. You have to kind of think about this the second postulate a little bit because it kind of seems obvious, so why are we making a big deal about it? But both these seem like pretty reasonable things to assume about any physical theory. And so Bell then said, okay, if we have these two postulates, what are the consequences of this? So, imagine now we run a series of experiments where we send two particles to Alice and Bob, and Alice and Bob either measure in basis A, Alice measures in either A or A prime, Bob measures in either B or B prime, and we can then get measurement results from this. So if we can imagine then that the outcomes of this experiment are basically random numbers, so random variables where the subscript n here refers to the nth iteration of the experiment, and each of these measurement outcomes has value either +1 or -1. And according to the postulates of this local determinism and objective reality, we can basically reasonably then say that there exists some joint probability distribution on these four variables, and consequently we can define a function which we will call g of n that depends on these four random variables. And we can then ask what possible outcomes this random variable g, which is dependent on these four fundamental random variables, has. So there are, for any given experiment, 16 possible outcomes, because we have four random variables and they're basically binary variables. So 2 to the 4 is 16. And we'll find that if you enumerate all of those, that g of n always either takes on the value +2 or -2. So that's pretty simple. You can then ask, if you have this random variable g, and you now take an average over many runs of the experiment, which here is big N, what is the absolute value of this average? And it turns out that, unsurprisingly, because the value for any given run of the experiment is either +2 or -2, is that you have this inequality where the average, the absolute value of the average, is less than or equal to 2. Of course, because the value can never be more than 2, it's unsurprising that it's bounded like this. So this all seems fairly mundane. Why are we going to such a big trouble of defining a bunch of things and whatever, when all we have is four values, and seems like we're doing a lot of mathematics for something that's very obvious. Of course it should end up coming out less than equal to 2. Why did we do this? So it turns out that if you then take a quantum mechanical state that looks like this, which is, this one here is, if you think about the 0 and 1 as being a polarization, where 0 is H and 1 is V, this is like H V minus VH state. And you ask the question, what does this G function look like if you do this experiment, sending this state to Alice and Bob? It turns out that you end up getting this expression here, where the angle theta refers to the angle of the diagonal basis. So it's not just H and V and D and A, but H and V and then some basis that's offset from H and V by an angle theta. And this is the expression that you get for the value of the average of G. And if you look at this, the plot of this state of the x-axis is this angle theta, and the y-axis is this average of G, you'll see that this red line here marks the value 2, that for some values of theta, you actually get a value of G, or an average value of G, that's above 2. And that's really remarkable, because we just saw at least the intuition for how Bell came to conclude that the average value of G must be less than or equal to 2, using two very simple postulates. So something interesting is happening here, is that if our understanding of quantum mechanics is correct, and I didn't give you the derivation for where this comes from, but if you're curious about it, you can come speak to me afterwards. It's maybe a page of mathematics to derive this from standard rules in quantum mechanics that people developed in the 1920s, that you end up finding that there are configurations where you actually violate this Bell inequality. And that's what the hackathon is about. The hackathon is about running an experiment where you set up the experimental apparatus with this angle theta such that you can expect a violation, and seeing that you actually do find a violation of Bell's inequality. And the philosophical conclusion of this is that, well, people in 1982, in the first instance, ran an experiment like this, and they found experimentally that really you do violate this inequality. You do get some values of G that are above 2, and that this really happens. So what are the implications of this? And it's that one of the two assumptions that we started off with must be wrong. Either physics must be non-local, and Bell was one of the people who believed this. It sort of really violates some of our notions of common day intuition that locality isn't as sacrosanct as we think, but maybe it's true. And the alternative is that this objective reality requirement must be broken. And both of them seem like reasonable things to start off with, but one of them is wrong, at least. So that's the philosophy side of it. So it turns out that there's some connection between Bell's theorem and the Eckert protocol. One of the sort of more practical aspects of it is that if you find a system, for example, you propose to use some spontaneous parametric down conversion source, and you find that it violates Bell's inequality in an experiment like the ones that the guys are doing in the hackathon, if it violates it, then it's actually a good source to use for QKD, and it's, in some sense, will be secure. Or at least it's a good candidate source where you can start off with that. If it doesn't violate Bell's inequality, then you have problems. So it's a necessary but not sufficient condition. And then another connection is that in Eckert's original paper for proposing his protocol, he actually proposes using Bell inequality violation as a means to test eavesdropping, because it turns out that in some configuration, if you have an eavesdropper, if they get gleaning a significant amount of information, that if you then test for Bell inequality violation in your system, which you should have, and if you don't find it, then it means somebody's eavesdropping. So that's another kind of neat connection between these two pieces of physics. So the final thing that I want to tell you a little bit about is quantum repeaters. So if you have an optical fiber and you send a single photon down it, typically after 100 or 200 kilometers, even at telecom wavelength, there's sufficiently high loss that you have a very low probability of actually receiving a photon at the end of the fiber. It will have been absorbed somewhere in the sort of fiber optical material. So this is a problem because we want to be able to communicate securely over distances much longer than 200 kilometers typically. And one proposal for dealing with this is by having a connection of different of intermediate stations, and you can do the BB84 protocol between each station and then XOR everything with each other and chain it like this. But this has the problem that then every 200 kilometers you need a physical location that you can actually trust, so people that you can trust with guns and so on. And this is definitely not ideal. So people came up with a different way of doing things, and this is actually the reason that people like the Eckert protocol. So far I haven't really given you any advantage that the Eckert protocol has over BB84, and it's technologically a little bit more difficult because you need this entangled photon source rather than just a single photon source. The reason that it's favored, at least in some circles, is that it can in principle be used in a way that can scale over arbitrary distances. And people have developed a so-called quantum repeater technology in principle that lets you connect different stations every 100 or 200 kilometers in a way that if there's an eavesdropper, you will be able to detect it. So again, you can make these repeater stations and you don't need that. Well, it's preferable that they be physically secure, but if someone breaches the security, you'll be able to tell, so they don't need to be manned. The downside of it is that building a quantum repeater turns out to be very, very difficult. We have QKD companies doing these BB84 protocols now, but building a realistic quantum repeater is probably something that may only happen in 50 years' time. It turns out to be almost as difficult as building a full quantum computer because of the error correction requirements that you have. But I thought I'd add it in there just as some curiosity so that if you see some news about what people are doing, this is the context in which everything is happening at the moment. So with that, I'd like to thank you for your attention, and I'm happy to take any questions now. I guess we have another 5 or 6 minutes in the official time, and then I'm happy to take questions and answer any queries you have afterwards as well, so feel free to find me after the talk today, or I'll be around tomorrow as well. So thank you very much.
Great, thanks, Peter. Questions?
Hi. In the BB84 protocol, when you mentioned that Alice and Bob then exchange and see which polarization type they are using to detect it, how do they do that?
This can just happen over a classical channel. They can call each other on the telephone, or they send each other Skype messages. Any classical communication channel is fine, and it doesn't have to be secure.
Hello. Can you tell us more about the hacking that's been made by Vadim from University of Waterloo, attacking the single photon sensor?
Sure. So what I've told you in this presentation is basically just the bare bones of the physical intuition for how these kind of schemes can be imagined to work. But of course, in practice, there's no such thing as a perfect single photon source, a completely lossless quantum channel, a perfect single photon detector, and so on. And so a bunch of people, ever since the advent of the commercial companies, at least, and probably since the first academic efforts, people have wondered how secure are actual practical implementations of BB84 QKD? Because if everything in principle works, that's nice, but if in practice any physical implementation has some defect that allows it to be hacked, then it's no better than the cryptography schemes we have now, and maybe a lot worse. So people have spent a lot of time, and there's this continual sort of chase of people come up with a scheme and some implementation, and then people try and hack it, they find some defect, and then people find a way to fix it, and so it continues. And an example of the kind of thing people have done is they figured out that in a lot of the detectors that were being used, you can sort of trick Bob's detector into thinking it sees things that it didn't actually see, and so on, by sending strong pulses down the channel, the so-called blinding attacks. And there's a whole range of these things where any physical non-ideality you can imagine in these systems, people will try and think of ways to exploiting it. And it's not clear to me, and I think most of the community, that really the commercial efforts yet have really proved that a determined adversary will not be able to defeat their system. It's this continual leapfrogging effect, and maybe they never will. It'll be just like security in classical computer systems, is that you show that you are secure against everything people have done up until now, but that doesn't stop somebody from tomorrow saying that, okay, in practice your system has this flaw. So it's ongoing work.
Hello. I don't know if you're the right person to ask, but I'm curious about this hackathon going on. I don't know if you're connected with that in any way. When are we going to hear about the methods they're using and the results they're getting?
I'm not sure. I guess Sebastian might be able to tell you some more.
Unfortunately, the last news are that there are some material hardware problems. The guys do not have the right detectors. So I don't know if it will be done, unfortunately.
But nevertheless, they have some stuff set up in the other
Yes,
building,
yes.
and you should go check it out anyway. 'Cause they-
Emission side. I will check, but
Regarding the random number generation,
Mhm.
how can you be sure that the measurement device or the polarized photon generator isn't biased? Is it like with classical random number generators that you make statistical analysis on the source? Or
Oh, sure. So one of the ways people have tested people have made quantum random number generators for a number of years now, and one of the ways that they've tested it to try and show that it's working as expected is they run it through the standard gamut of statistical tests, showing that it's as random as the tests can determine, and they pass these tests. But you can imagine biases, but these experiments are very simple. So the room for biases is kind of small. Basically, if you take a polarized photon source and you put it into a polarizing beam splitter and you have two detectors on the output, and at each time slot when a photon comes, you either get a detection on the H port or the V port. That's your random number generator. So there's not really so much that can go wrong, and the main deviations will not be so much in randomness, but in the distribution that you produce. For example, let's say your polarizing beam splitter has some bias where actually it lets through more H photons than V photons. It's not completely accurate. This is equivalent to the polarization state going into your PBS is a little different than you thought. Then you will get some distribution where you have more ones than zeros overall. So it's now not a uniform distribution of 0 and 1, but it's still completely random. But people, of course, want to test that their devices work properly, so they run it through these tests, and so far everything that has been produced properly passes these tests.
I have a second question. Isn't there a way to make weak measurements that don't collapse the state?
So the notion of weak measurement in quantum mechanics is a little bit misunderstood. So it's not that it doesn't collapse the state. It's just that it doesn't collapse it completely. It's a little difficult to understand in terms of polarization, because polarization is really binary. So if you do this, you can really think of it as collapsing it. But imagine you do something like you have a quantum particle that has a position and a momentum. You can imagine measuring this. You can imagine measuring, for example, the momentum of the particle, but not very accurately. And so you get an answer back, but you're kind of uncertain about it, so it collapses it, but kind of weakly, because you didn't get a very accurate answer back. That's the best intuition I can give in a short amount of time for how a weak measurement works, is that it's doing sort of a very uncertain probing of the quantum state.
Any other question?
So the security of a quantum K distribution system relies on the property that a measurement collapses a state. And measurement, it's a kind of interaction. So the question is, we do a lot of interaction with these photons. So beam splitters, we pass them through fibers and so on. And of course, the photons interact with the medium and so on. Why does this interaction not collapse the state?
So the property of the photon that you're typically measuring in this is the polarization. And it's indeed very important that when you build these systems, that you use components that maintain the polarization properly. But it turns out that there's a large industry that produces these kind of things. So for example, if you do QKD with fiber, you can buy polarization maintaining fiber that is, it of course has some specification, but up to some very good specification, if you send a linearly polarized photon down it, it will come out with the same polarization that it entered with, and that it doesn't get collapsed to to some state. It doesn't get manipulated. And people build these systems out of these specifically chosen components where they don't have these unwanted interactions.
So it is a property of interaction. An interaction may collapse the state or may preserve it.
Yes, although in the case, like if you think of the example of the optical fiber manipulating the polarization state, what does measure really mean there? Well, okay, it can measure the polarization of the state, but what basis does the environment measure it in? It can kind of do it in a continuous basis, so it's changing it in basically an arbitrary angle, and that's why these specs, which tell you about the polarization coming in versus out versus going in, basically tell you how strongly it's being measured within the fiber.
Okay, thank you.
Okay.
Anyone else? Okay, well, thanks, Peter, again.
All right, thanks very much, guys.